We have a linear system here. It's actually three equations and three unknowns. And one of the techniques to solve these types of equations is called Gauss-Jordan elimination with an augmented 3x4 matrix. Remember that in a matrix, we are going to perform elementary row operations. And there's three of them. Okay, we could interchange any two rows. We could scalar multiply a single row and store it in that single row. Or we could multiply a single row and add to another row. Okay, so the general strategy for a 3x4 augmented matrix is we want to first have that leading one in the upper left-hand corner. Then we want the zeros right below it. So we often pivot from row 1 to get this first zero and then this second zero. Then the fourth thing we want to do is probably try to get that leading one. And the fifth thing is probably try to get that zero right below it. And then finally the sixth position, we'll try to get that 1 there in the lower bottom right. Now, these do not have to occur in this numerical order. This is just a general strategy. In fact, most people will probably get to the destination differently. Okay, the key is that we'll perform all three elementary row operations along the way, but there isn't a perfect procedure. Okay, so you just have to strategize. And then another thing you want to do, a hidden strategy, is avoid adding fractions as long as possible. You don't want to be adding fractions right away when you're solving systems with matrices. So why don't we get started? Let's draw our 3x4 augmented matrix. So we draw a bracket, 3, -2. We have 0 z's in that first equation. We're going to draw a vertical bar to separate the coefficient matrix with the numbers on the right of the equal sign. So a 0 here. And there we go. We have our 3x4 augmented matrix. So we don't want to introduce fractions. A common mistake here is somebody might want to go 1/3 times row 1. But if you do that, you're going to introduce fractions in row 1. So we're going to try something else. We're going to avoid adding fractions as long as possible. So we're going to do negative row 2 added to row 1. And then we'll store in row 1. Remember that tilde means row equivalent. Now, row 3 doesn't change, so I'm going to copy that down first. That way, if you copy the rows that don't change, you'll less likely make a mistake. Row 2 doesn't change either, so I'm just going to copy that from the previous matrix. Now we're ready to do some operations. Negative row 2 plus row 1. So I get our leading 1 there. Now we have -3. We have 2. And now we have 1. Now we want the 0 right below that leading 1 in the upper left-hand corner. So why don't we do -2 row 1 added to row 2. And now we store in row 2. If we're storing in row 2, that means row 1 doesn't change. And row 3 doesn't change. Now we're ready to get this to be a 0. We have a 7 there. We have a -6 here. And then you get a 0 here. Once again, we don't want to introduce fractions. So let's strategize. Let's do 3 times row 3 added to row 2. put my tilde up here. So row 1 doesn't change. Row 3 doesn't change. But row 2 does change. In fact, we get our 1 here. We get a 3 there. And we get negative 27. Making very good progress. Now, let's try row 2, add it to row 3. Restore in row 3. That means row 1 and 2 don't change. Once again, copy the rows that don't change. You'll less likely make a mistake. And be very neat with this process. Negative 54 minus 9, negative 63. This is looking better and better. 1/9 times row 3. Now this matrix is row equivalent. To this new matrix. Okay. Why don't we do 3 times, oh, not 3. How about negative 3 times row 3 and add it to row 2. I'm actually going to perform a pivot here. Notice this is still another single elementary row operation. So we're going to do negative 2 row 3. Row 3 wasn't going to change anyway. And I'm going to now add it to row 1. These are still 2 single elementary row operations because here the storage is different. We're going to store in row 2 and store in row 1. So we're okay to do that as long as you don't overlap those storage compartments. So row 3 doesn't change. Row 2 is going to change. Made that a 0. So 21 minus 27. Now we're going to change row 1 as well. Negative 2 added to 2, we get 0. Negative 2 added to 2, we get 0. 14 added to 1, we get 15. We're almost done. We need now a 3 times row 2 added to row 1. And let's see what magical matrix we get now. Negative 18 added to 15. Oh, did I forget something? I must have forgot the negative 6. There we go. Now remember, in Gauss-Jordan elimination, we read from the bottom of the matrix all the way to the top. So this really says z is equal to negative 7, y is equal to negative 6, and then x is equal to negative 3. Now let's write our set consisting a unique solution. It's consisting a unique ordered triple.